Okay, so we are in section 10.3, arc length and curvature, and we talked about how to find the arc length of well, you have a space curve, and from a certain time to another time, it traces out. You have an arc, right? Space curve is an arc in space, and you can find the length of that arc using the formula. Well, using this formula here. And sometimes you can find the exact value of the arc length. Other times you have to use your MATLAB to do an integration. And we talked about that in the last class. And so moving on in section 10.3, they make a comment here about parameterizing a curve with respect to arc length. To be honest, it's not something I've done in my work in math, but they say it's often useful to parameterize a curve with respect to arc length because arc length arises naturally from the shape of the curve and does not depend on a particular coordinate system. So if the curve is already given in terms of a parameter t, and S of t is your arc length function, okay, let me just highlight it all here, then if that's the case, that a curve is already given in terms of a parameter t, and S is the arc length function, we may be able to solve for t as a function of S. Then the curve can be reparameterized in terms of S, okay, and that would be your parameter. Okay, so you're basically expressing your space curve in terms of the parameter S, and S stands for arc length. So in example 2, they want you to reparameterize this helix with respect to arc length measured from 1, 0, 0 in direction of increasing t. And so what they do is they say, well, all right, we have established that the derivative of arc length with respect to t is a constant, square root of 2. And so then the arc length itself would just be equal to square root of 2 times t. And that means t is equal to the arc length over, hold on here, t is equal to the arc length s divided by square root of 2. And so you can substitute in for t, s over the square root of 2. And that's, you'll get this reparameterization of your arc length. You'll get your reparameterization of your curve, of your space curve. So parameterizations are never, for space curves, are never unique, you know. It's just like you learned, for instance, we talked about this, the parameterization for a line in space. You could have infinite number of different parameterizations. But of course, in this example, they're actually changing they're using a new variable s instead of t, but that's okay. And it's something that I've not seen in my practical work in math, but I can imagine it would be something that could come up. And you know, that's why it's good that you're aware of it, and you'll have a homework problem or two on this. All right, well, are there any questions on that before we move on? All right, well, let's go ahead then and move on and talk about curvature. Curvature. All right, so hold on, I want to highlight this if I can. So parameterization is called smooth on an interval if its derivative is continuous. A curve is called smooth if it has a smooth parameterization. A smooth curve would have no sharp corners or cusps where the tangent vector turns. It does so continuously. All right, and they talk about here a tangent vector. So the tangent vector t, so like r prime of t, the derivative of your space curve is r prime of t, and r prime of t is tangent to the space curve at time t. But this, as you know, but this tangent vector t, capital T, is defined as the r prime of t divided by the magnitude of r prime of t. Okay, that's how the tangent curve is defined. And what would the length be? What would the length? So it makes sense that this, you know, if you're talking about a tangent vector to a space curve, it should be a multiple of the derivative vector of the space curve, and it is. The tangent vector t is just a multiple, 1 over the length of r prime of t, times the derivative r prime of t. R prime of t is tangent to the space curve, so the tangent vector has to be a multiple. This tangent vector t must be a multiple of r prime of t. But what's the length of the tangent vector t? What's the length equal to based on this definition, this highlighted definition? If you were to take the length of t, what would it have to equal? In other words, what I'm saying, let me rephrase it. Let me rephrase it here. So, whoops, hold on. Maybe I'll do this in black. Here's the tangent vector. It's defined as r prime of t divided by the magnitude of, or the length of that derivative vector. And what I'm saying now is, suppose I want to know the length of my tangent vector. Well, that would be the length of r prime of t divided by the length of r prime of t. What would this equal, class? Well, would this be, it would equal 1. That's right, Ryan, because I can bring out, I mean, this here, the length of r prime of t is just a constant, so that can be brought out. And you have this. So indeed, it equals 1. Okay, are there any questions? That's why they're defining that the tangent vector is a unit vector. We call it a unit vector because it has length 1 for any value of t, by the way, for any value of t. By the way, is this unit tangent vector orthogonal to its derivative for any value of t? Well, what's true about the length of this tangent vector t. The length is equal to 1, and 1 is a constant, right? It's not dependent on t. 1 is a constant. So when we have a space, a vector function that has constant length, then we learned that the vector function would be perpendicular to its derivative. So this is another nice quality that's going to be very handy for us in regards to this tangent vector t. All right, are there any questions on that? Okay, Diodath is good. And all right, well, let's move back. Let's go back to the book here then. Back to the book. That's not the book. Hold on. Okay, so now we're back in the book. And they show here in figure 4 a space curve C in three-dimensional space, and they show just some unit tangent vectors along the space curve, equally spaced. They all have length 1. So let me ask you a question here. Let me ask you a question. So I wish we could draw on this. All right, so the curvature of this space curve is, where is the curvature? Let me see here if maybe, hold on, class. No. All right, let me go back to the, you see that space curve. Okay, I'm going to go to the whiteboard here, and I'm going to redraw that space curve. It's not perfect, but there you go. All right, this is a space curve C from figure 4 in the textbook. And I'm going to put some dots here. I'm going to put, okay, this is dot 1. Okay. Hold on here. And this is dot 2. Okay, and got to be a little careful here. I want to make sure it's very light. Okay. So I have 2 dots, dot 1 and dot 2. And incidentally, on each dot, I can draw a tangent vector. Okay, and then, you know, I can draw another tangent vector nearby too. Sorry if it isn't, perfect. All right. And so I'm wondering, where is the curvature higher? At point 1 on the space curve or at point 2 on the space curve? Where does the curvature seem higher? Okay, and I'm going to put a black dot here where this other tangent vector is. Okay, I'm getting a lot of correct responses here. So you have a good feel for this. Good, everybody. Clearly the curvature is greater at that second point. It's greater here than it is here. And intuitively, you have an idea of what curvature is. But you see, what you could think about, well, what's true about the tangent vectors near, and again, these are tangent vectors t. Okay. What's true about the tangent vectors at point 2 compared to point 1? The tangent vectors, I've drawn 2 of them at near point. I drew one right at the dot at point 2, but then one a little further away. And then at point 1, I drew a tangent vector right at the red dot, and then I drew another tangent vector at the black dot a little further away. What seems to be happening at point 2, those tangent vectors, compared to point 1? The tangent vectors seem to be doing what more? They seem to be spreading, or I was thinking of another word, but I know what you mean. Changing more. That's right, Ryan. They're changing more, changing direction. So if we were good, everybody. So if we were to think about how the tangent vectors are changing with respect to time, over the same length of relative to how the arc length is changing with respect to time, because for both points 1 and 2, the arc distance is the same. So ds dt, I got to be a little bit careful. There's a relative to like some point before. You have an arc length, and then you have another arc length. But relative to the length that we move along the space curve, does it make sense that the change in the rate of change of the tangent vector with respect to time, hold on here, we can make that a little better. Does it make sense that the rate of change of the tangent vector with respect to time divided by the rate of change of arc length with respect to time would be greater at point 2 than it would be at point 1? Okay, there you go. Well, that's how we define curvature. In curvature, we use the Greek symbol kappa to define curvature. This is the formal definition of curvature given in your textbook, definition 8 on page 709. I'm trying to justify why they use that definition. And intuitively, you know that. Intuitively, you're actually applying that definition because you're saying, hey, yeah, the curvature is greater at the second point than it's greater at the second point than the first point. Okay, so are there any questions before I go back to the book?
I have a question.
Yes, Ryan.
Could it be considered the second order derivative of S? Or is that
The
wrong?
second order derivative of S?
Yeah.
Well, we're not looking at concavity. No, no. Since we're working with a space curve, we have to involve a vector in there somewhere. When we're dealing with, so I'm not. Your question's actually a good one. You're saying like the rate of the rate, but we're just dealing with how fast are these tangent vectors changing relative to the arc length changing over a period of time. That's really what we're doing. It's really that simple. Now, could there be further? I mean, there are further definitions of the. And actually, I want to say this is a function of t here. The curvature is a function of t. Curvature, kappa. There can be other than definitions. There are other definitions actually of curvature, but this is the one we start with. If you look in the book, they'll give some other definitions of curvature that derive from this. And for the special case where you have a function f of x, okay, where you're dealing like in the xy plane, function f of x, then the curvature as a function of x would be dependent partly on the second derivative. So that's a good insight. That's Formula 11 actually, Ryan. And I'm going to let you, you're welcome to look at that. But you know, your insights are good. Your insights are good. And you know, the DTs cancel out. See, we basically we actually talked about this definition of curvature and got to that formula on the right, and then that formula on the right, dt over ds dt, would just be then the absolute the length of that would just then formally, you could express it this way. Okay. And a circle, for instance, has constant curvature. A circle would have constant curvature because look at the hold on here. Let me get it on the. You have a circle radius A. That's how it's parameterized, and the derivative of the space curve for a circle in the xy plane is given as you see here. The length of that derivative is going to be equal to a, and so the tangent vector would just be taking the r prime of t and dividing it by a, and that's going to give you this tangent vector, but then the derivative of the tangent vector would be this. It's just really computation. And so then the curvature is going to be equal to the derivative of the tangent vector divided by, I'm sorry, the curvature would be the length of the derivative of the tangent vector divided by the length of r prime of t. And that's just going to equal 1 over a. Okay, so does it make sense that if you move around in a circle, the curvature is going to be constant? Does that make sense? Okay, makes sense to, good. Now what happens to the curvature as A gets larger? For this example 3 that we're looking at. What happens to the curvature? it decreases. Absolutely. And that makes sense, because if the radius of the circle gets larger and you're traveling in a circle with a larger radius, are you going to feel the curvature as much? I mean, think about like driving around in a circle. Like, think of your bicycle driving around, like riding around in a circle, or a car moving around in a circle. Won't the curvature be less if the circle's greater? I mean, think about going around in a circle in your car. Are you going to feel it more if the circle? Yeah, you're going to feel it more if the circle has a smaller radius than if the circle has a larger radius. And in fact, when we get into section 10.4, we're going to learn that acceleration, the acceleration vector, is dependent on curvature. And so it's important that we talk about curvature. It is important that we talk about it. It's a pain in the neck to compute sometimes. It's great if you have a circle or a helix, but for something else, the formulas can get, the answers can get complicated. But nevertheless, we have to understand it. All right, are there any questions before I move forward in section 10.3? Okay, well, let's keep going here. All right, and I notice we maybe have, we have 17 people in the class. Usually we have, so I mean, with everybody here, me being here, we might have more people than in the class. So we might have a visitor. So I'll say hello, visitor, if we have a visitor here. Okay, no problem. So, okay, now, you know, there are other formulas for curvature. This is a formula for curvature where it just involves computing the first and second derivative of your space curve. Okay, so sometimes that formula is more convenient to use than other formulas. Okay, and that's really, you know, the main thing in terms of curvature, I think, and they talk about, they go through a proof. I'll let you look at that. They have an example where they find the curvature of a twisted cubic. I'll let you look at that, class, because well, I mean, here in this problem, they just use the formula, example 4. They just use the formula that is in, that you saw previously, theorem 10. It's not a big deal, okay? It's just computation. Let's keep moving on here, because we have a lot to get to today, and I want to hit the some other important topics. Okay, so now this is important here. Normal and binormal vectors. So here in figure 6, you have something called a TNB frame. Okay, a TNB frame. Okay, you have a space curve, and you have a point on the space curve, and drawn on the space curve are a tangent vector t, and that t is a unit tangent vector. And then you have these other two vectors, also a normal vector n of t, and what's called a binormal vector b of t. And together, these three vectors form what's called the TNB frame. Okay, TNB frame. So, yeah, they talk about it a little bit down here. Okay, so, hold on here. Let me just, oh, I don't want to do that. Hold on. So, oh, okay, I'll move this over here. So figure 7 illustrates vectors t and b. Okay, at two locations on a helix. And we'll go back to the example, but I just wanted to show you it forms what's called the TNB frame, and it plays an important role in the branch of mathematics known as differential geometry and in its applications to the motion of spacecraft. Okay, so now let's go back a little bit. Let's go back a little bit. Okay, and how is this normal vector defined? Well, the normal vector is defined as the derivative of the unit tangent vector divided by the length of the unit tangent vector. So the normal vector has length 1 also. Okay, the normal vector has length 1 also. And then the binormal vector here is defined as the cross product of the unit tangent vector and that unit normal vector. Does it make sense in figure 6 that the binormal vector is perpendicular to both the tangent and normal vectors? Does that make sense? Absolutely it does. We know, thank you Jamal, thank you Ryan, thank you Diadath. We know the cross product of two vectors is going to be orthogonal to the plane that those two vectors are in. So the cross product of the tangent and the normal vector, the unit tangent and the unit normal vector, I should say, is the binormal vector, and that's going to be perpendicular to the plane at which those two vectors are in. Okay. Now, incidentally, does it make sense that the normal vector, in the picture, you notice that the normal vector n of t is perpendicular to that tangent vector to the space curve? Does that make sense? Does that make sense that it should be? Yes, it absolutely makes sense, because we know that because the tangent t vector is a unit vector, the tangent t vector is going to be perpendicular to its derivative. Well, the normal vector here, the normal vector n of t, is just a multiple of the derivative of the unit tangent vector. And so it's going to be orthogonal to the tangent vector also. Okay, so this is a really important concept in section 10.3, a very important concept. And we're going to actually do a problem here. They do an example here where they compute the tangent normal vectors, but we're going to, that's example 6, but we're going to do a problem where we do that also. So let's just move on here, because I want to get to an actual example where where you formally put it in your notes. But I'll mention another thing here in regards to this TNB frame. So there are two planes in this TNB frame that we care about. One plane is the plane formed by the tangent, the unit tangent, and unit normal vectors. That plane is called the osculating plane, because that plane kisses the space curve, essentially. It's called the osculating plane. And they mention this here. The plane determined by the tangent, the unit tangent, and unit normal vectors is oscillating. It's an oscillating plane. It comes from the Latin word osculum, meaning kiss. Okay. But there's another plane of interest too, the plane determined by the binormal and normal vectors. That's called the normal plane. Okay, that's called the normal plane. Okay, of the space curve at point P. So you have an osculating plane of the space curve at a point, and you have a normal plane of the space curve at a point. And the normal plane here, formed by the unit the unit normal, and the binormal vector is also going to be a unit vector because it's the cross product of unit vectors. The binormal vector and the normal vector together, those two vectors, the plane that contains those two vectors is the normal plane. And I think of the normal plane as like chopping the space curve at the point P. That's what the normal plane does. It chops the space curve at the point P, a vertical chop. All right, so on that note, I'm going to work through this example 7 here. So let me go ahead. Are there any questions so far? All right. With that, let me bring up an example here. And let me give you a moment to copy this example down in your notes, okay? All right. Okay, so what we want to do is we want to find equations of the oscillating plane and the normal plane for this helix at the point 0, 1, and pi over 2. Then we want to find the curvature of the helix as well. Okay, so I think you can imagine this helix. You know, this helix is a space curve. As t increases, it goes up. You know, this is your helix. I tend to like to put my space curves in red. Let me do it in red here. And that wasn't a very good picture anyway. Better picture, class, of a helix? Okay, thank you. All right. Okay, there's my space curve. And what would you guess about, by the way, the curvature for this helix? Do you think the curvature is going to be constant for the helix? All right, your intuition is let's see. Ryan and Eric think yes. It's always good to use your intuition. All right, well, let's go ahead and find the equations of oscillating and normal planes. So first of all, what I do is I have to take the derivative of my space curve. My space curve, recall, had components cosine of t, sine of t, and t. So I take the derivative of the components and get r prime of t. The unit tangent vector is going to equal 1 over the square root of 2 times negative sine of t cosine of t and 1. Is everybody okay that the magnitude of r of t, hold on now, I might have, let me check one thing. There should be a prime here. There should be a prime here, sorry. There should be a prime there, right? Okay. So I think it's no problem for you to, you know, the length of that is going to be square root of 2 because negative sine, the quantity negative sine squared plus cosine squared plus 1 is equal to 1 plus 1 because sine squared plus cosine squared equals 1. You get the square root of 2. Now I need to get the derivative of the tangent vector. Well, the derivative of the tangent vector, this 1 over the square root of 2 just stays out in front. Okay, that just stays out in front, you know. And the derivative of minus, hold on here, the derivative of minus sine, cosine, and 1 are as you see here. A little note, by the way, the derivative of unit tangent vector t is perpendicular to the unit tangent vector t because the length of that unit tangent vector t equals 1. But in order to find the equation of the oscillating plane, I need to find the unit normal vector also. Well, the unit normal vector is defined, of course, as the derivative of the unit tangent vector over the length of the unit tangent vector. Okay. And let me just see here. That's going to equal the vector negative cosine of t, negative sine of t, 0. But let me just see one thing here, class. I'm just looking at one thing. One moment here. Let me, one moment. I want to check. I want to check one thing. So you're right here. You're right here. Okay. You're right here. One moment, class. Let me get this here. Yep. Yep. I had my phone on vibrate, but it was ringing, and I don't want it to ring while class is going on. I don't want it, so I put it in another spot here. Let me just go to the whiteboard for a minute here, class. Okay, I want to take a look at this real quick. Let me try out my hold on. Try out my little pad here. One moment. Okay, let me just see here. All right. Okay, so the tangent vector was equal to 1 over square root of, no, I'm talking about the derivative here. Okay, it was equal to 1 over, the derivative of the unit tangent vector was 1 over the square root of 2 times minus cosine of t times minus sine of t and 0. All right, now the magnitude of that vector would be 1 over the square root of 2 times the square root of negative cosine of t squared plus negative sine of t squared, right? Got to turn my chair. I got a chair has an arm on it, so I got to move it a little bit so I get free. All right, so this is a negative here, right? Okay, so this all equals 1, and so I get 1 over root 2. So far, are there any questions? All right. Well, what's going to happen is when I divide the derivative of the tangent vector, the unit tangent vector, by its magnitude, the 1 over root 2's are going to divide out, right? Well, I should say here's 1 over root 2, right? The 1 over root 2's are going to divide out. And so, let me just see here. I don't necessarily want this circle, but you know what I mean. You know what I mean. Sometimes it's better to use the mouse. Okay, so again, I'm going to find the normal vector, n of t, and to do that, I got to divide the derivative of the unit tangent. Sorry, I got to divide the derivative of the unit tangent vector with its length. And when I do that, the 1 over root 2's here are going to simplify out. And so what will happen is then the normal vector, which is the derivative of my unit tangent vector over the magnitude of, or the length of the derivative of the unit tangent vector, that's just going to be equal to then the negative cosine of t, negative sine of t, and 0. Okay, is that okay? Are there any questions on that? The reason I'm doing that is I didn't, all right, Ryan's good. In the work, I didn't, I'll show you where I'm coming from. May I move back to the example? Everybody's good here? Okay, all right. Very good. Then back to the example here. Okay, so here I didn't really. I guess this step here is not really. It's kind of confusing a little bit. You can just go from here to here. Okay. So now t equals pi over 2. So at the point on the helix, we're talking about the point 0, 1 pi over 2, because the z coordinate is the z coordinate's pi over 2. Well, t is the z component, so that means t has to equal pi over 2. And so the sine of pi over 2 would be 1, and the cosine of pi over 2 would be 0. So that's why t equals pi over 2. So, you know, at the point 0, 1 pi over 2, t equals pi over 2. And so the binormal vector at pi over 2 is going to be the cross product of the tangent and normal vectors at pi over 2. And so, well, the tangent vector at pi over 2, the unit tangent vector at pi over 2, has a 1 over root 2 in front of it. But when you do the cross product, there's a property that if you have the cross product, hold on, if you go back to section 9 point, let me see here, cross product was section 9.4. If you go back to properties of the cross product, one of the properties was that in section 9.4, it's the second property. Let me just see, maybe I can, hold on. One of the properties was that if you have C, constant C times A times the cross product B, okay, that equals C times the cross product of A and B. And that's what we utilized here. Hold on. Now let me switch back to the, that's what we utilized here. Because that's what we utilized going from here to here. We utilized that rule. Are we good on that? So the cross product of a constant times a vector A times a vector B, thank you, Ryan, equals the constant times the cross product of A and B. That's what was done here. It's a helpful rule to know because then you don't have to carry that 1 over square root of 2 out in front of the, you don't have to carry it out when you do your cross product. And then using the, you know, the rule, you're going to get 1 over root 2 times 1, 0, 1. Okay. So now we've identified, this is a vector here, by the way, right? We've identified the binormal vector at t equals pi over 2, the tangent vector at t equals pi over 2, and the normal vector at t equals pi over 2. And these are all unit vectors. They form the TNB frame. And once we have that, we're able now to find the equation of the osculating plane and the normal plane. Okay, so which of these, you know, you have vector 1, the binormal vector, vector 2, the unit tangent vector, vector 3, the normal vector. Which vector is used to find the osculating plane? Which vector? We have a point on our plane because the osculating plane, the point is on the space curve is 1, 0, 1 pi over 2. All we need now is, and the plane, the osculating plane contains that point. All we need is a perpendicular vector. Hold on, which, the binormal. Very good, Diodath, the binormal. So the binormal vector is the binormal vector is the square root of 1 over 2 times the vector 1, 0, 1. Do I need to use this square root of 1 over 2 that in front here? Do I need that? Or can I for my perpendicular vector, or can I just use the vector 1, 0, 1? In other words, if I include the square root of 1 over 2 factor in front of the vector, my vector would be 1 over root 2, 0, and 1 over root 2. That would be my, I mean, that is the binormal vector. But for the purposes of, you know, a vector perpendicular to the plane, could I get away with just using the vector 1, 0, 1? Could I get away with that? Yes, yes, and that's what I do. So on the next page, and you don't have to copy this up here, we can go right to here. The equation of the oscillating plane at the point 0, 1 pi over 2, well, the normal vector is the binormal vector. What I mean is the perpendicular vector is the binormal vector, and we're using 1, 0, 1. Okay, 1, 0, 1. And then the point on the plane was 0, 1, and pi over 2. Okay. And so we get the equation of the oscillating plane, which we can write like this. And there's a figure, let me see. There's a figure 8 in the book. Yep, figure 8. It's not on page 714 though, it's on page 713. But don't worry about the page numbers, you know. I'll show you the figure in the book. But let's just, so here's the equation of the oscillating plane. And I drew a little picture here. We can get back to that. But for the equation, but now we want the equation of the normal plane. Okay, and what vector is going to be used? What vector is perpendicular to the normal plane based on the TNB frame? Is it the unit tangent vector, the unit normal vector, or the unit binormal vector? What vector is perpendicular to the normal plane for the space curve at the point 0, 1 pi over 2? It would be the tangent vector. If you look at figure 7 in section 10.3 in your ebook, or I should say figure 6, you'll see it's the tangent vector. Maybe I can hold on. Let me just show the book here real quick. It's worth showing it. See? It's the tangent vector that's perpendicular to the normal plane. Normal plane contains the binormal and normal vectors. So on that note, let me get back to the, always have to, back to the thing here. So the tangent vector at t equals pi over 2 is equal to 1 over the square root of 2 times -1 times the vector -1, 0, 1. But again, the 1 over root 2 is really irrelevant towards finding the equation of the plane. So we can just use -1, 0, 1. Those would be the direction numbers for our perpendicular vector. And therefore, here's -1, here's 0, and here's 1. And from there, you get the equation of your normal plane. It would make sense too that the osculating plane and the normal plane, those are perpendicular planes because the TNB frame forms a box, right? And what I did here is in this picture, I just drew XC plane and I drew the lines. Like pretend that the y-axis comes out at you. You can see that those two planes are perpendicular. Okay, and now what's left to find is the curvature, but are there any questions so far? May I move to the next page? All right, people are good. All right. So what's left now is to find the curvature. Curvature, okay, I have a formula, and don't worry about the page number. It makes sense to use formula 9, though. Formula 9, since I know what the derivative of my unit tangent vector is, and I know the derivative of my space curve, it makes sense to use this formula here. And that's what I do. Now what I have on the right, incidentally, is computing the curvature in MATLAB. So I don't have a formal program. You know where the MATLAB programs are in Blackboard. I don't have a formal program, but it's there written down here on this page, and it'll be in the recording if you care to look at it. I'm more emphasizing you finding curvature by hand, because your next exam, you know, I would want to see that work by hand. But it's nice to have a program to verify your answer, right? It's nice to have a program to verify your answer. And so that's why I just thought, hey, why not have it there? To be honest, I've not used that program in a while, but it should still work, you know. And the commands are cool. You got norms, you know, to compute lengths and stuff. But again, you know, you want to be working your problems out by hand, because I want to be a little bit careful. You want to be working your problems out by hand because showing work's important for exams. But you know, it's always good to check your answers. And all right, very good. So this helix, it turns out it is going to have constant curvature, and it'll equal a half. Okay, let me know if you have any questions. I'll give you a moment to copy this down. All right, are there any questions in general on this problem? All right, that's comfortable. How many think offhand this is pretty cool? Pretty cool stuff. Great, great. Thank you, Christopher. Thank you, Ryan. Okay, thank you, Naima. Very good, very good. All right, well, what I want to do, I want to give you 15 or 20 minutes for you to work a little bit on the 10.3 exercises, the second batch. Okay, so let me just go into my math lab here. I want you to focus on, and I know you have assignments due on Sunday, but I want you to focus on the on this second batch here. So let me go in here. One moment, class. Okay, so when you open up WebAssign and look at current assignments, do you see the 10.3 exercises, the second batch there? Excellent. Okay, everybody, I'd like you to work on those exercises for the next 15 or 20 minutes, okay? And then we'll move into section 10.4. So let's use this time as class time, work time. People are always, sometimes people always like more time to do homework, right? We always like more time. Hey, here's some time, okay? And I'm here to help you if you have a question. So I saw a big improvement on last time, the classwork time, doing the homework. So let's see what you can do here, okay? All right. Let me know if you have any questions. We're working on 10.3, the new assignment. Okay, so I'm seeing some scores here. All right, about another 10 minutes, and then we'll move on to section 10.4. Okay, a few more minutes, everybody. Okay, so I'm pleased so far. You're making some headway here, but we have to move. We have to now get back to the lesson. Let me. I don't want you to get distracted here. I'm pleased though so far. All right, so I'm gonna have to deactivate the assignment. Very good, but don't worry, I'll activate it after. And I want to mention section 10.4, which we're going to talk a little bit about now. There'll be an assignment on that due next Tuesday as well, but I still need to, figure out the problems I'm going to assign. So right now that's going to have you'll see 10.4 listed as an assignment, but it'll have a password on it. I'm going to tomorrow work on that assignment and get the password off. I don't think anybody will be working on that one right away. I think you're going to be working on 10.3, but I'll get that 10.4 assignment ready for you then, by tomorrow for sure. All right, I want to point out one thing, class, before we move forward here. So MATLAB assignments are a part of the 200 level courses. And what I'm doing here, if you go into, can everybody see the Blackboard okay? Blackboard page? Okay, good. So I need to thank you everyone, I need to get your MATLAB assignments, at least some of them posted, at least the first one, okay? And I am going to do that very soon. But I just wanted to give you an idea of terms of like due date and so forth, and how I'm not going to spend I'm just going to spend a moment on this because we'll talk more about it next week. But if you go under MATLAB assignments, okay, there's a blue link here that you click and you'll see MATLAB assignment 1. But I'm sorry, I just have not uploaded it yet. I was focused on trying to get good lessons ready, but I will have that uploaded by tomorrow for you. But at any rate, the MATLAB assignments right now, they're about 8, 7 or 8, maybe even 9 MATLAB assignments in this course. But the way the MATLAB assignments work is there's like there are documents. Every MATLAB assignment is a document that has examples. And then after the examples follows an exercise. So the exercise comes at the end after the examples. And what'll happen, so the MATLAB exercises are not ones where you got to go and do research and stuff like that. It's just basically study the examples in the document and then apply them to the exercise. But the way I prefer students do MATLAB assignments is I like students to work together. I like students to work in groups of 3 or 4. Now you can work on your own, but if you work in a group of 3 or 4, you're going to get extra credit. And it says here there's going to be 10% extra credit on your MATLAB score. Working in groups, I think, is helpful for MATLAB assignments because you can check your answers with each other. You can help each other. I just think it's a nice. How many have maybe done a computer project in the past where they worked with a few people and like as a group? Has anybody done that before? Okay, Deodath has, and Ryan has, and I was it helpful? Was it helpful, guys? Okay, good. Well, I excellent, and Eric has too. I'm happy to hear that, and I'm going to encourage you to work in groups of 3 or 4, and I will give you extra credit if you are part of a group, because I know working in a group takes a little bit of effort. You have to coordinate a time to meet on Zoom and all that to discuss the MATLAB assignments. So anyway, I just want to kind of give you a heads up on that. And, I think probably some of you know other people in class, but, if you need to get to make a few friends in class and so you can be in a group, that's fine. Sometimes I'll even have a student in class create like something on Discord like a thing where people can sign up to be in groups? Who's heard of that kind of thing in like in Discord? Has anybody heard of that? Okay, you have one. Okay, so you have one for the class. Okay, well, I'll let you all take care of that. You decide on your groups, and very good. All right, so and once again, I will get the MATLAB assignment one loaded by tomorrow for sure. Okay, so let us continue on. And Eric's asking if somebody can send a link in the chat window there, so that would be great. Let me just hold on here. Let me see. So I got to find. Okay, let me go back into here. We're moving into section 10.4. 10.4 deals with motion in space, velocity, and acceleration. And let me make this visible here. Let me stop the recording here. I think I forgot.